I want you to imagine that you are standing in a kitchen at midnight. On the table in front of you is a large glass jar. You know exactly how much water should be inside it because you watched the jar being filled earlier that day. But when you return, nearly half the water appears to be gone. The lid is still sealed, nothing has spilled, no one has touched it, and you weigh the jar. The mass tells you the water must still be somewhere, but when you look, you cannot see it. For decades, cosmologists lived with a version of this problem on the scale of the entire universe, not dark matter, something in a sense even more embarrassing. Ordinary matter, the same basic kind of matter that makes your body, the earth, stars, planets, dust, and gas. We knew how much of it should exist. The early universe told us, the cosmic microwave background told us, Big Bang nucleosynthesis told us, and yeah, when astronomers counted the matter they could actually locate in stars, galaxies, and known reservoirs of gas, a substantial fraction seemed to be missing. The accounting did not close, matter had not vanished, the universe had simply hidden it extremely well. Then astronomers began using one of the strangest signals in the sky as a measuring instrument. Fast radio bursts, millisecond flashes of radio waves arriving from distant galaxies. For years, these bursts were themselves a mystery. But eventually, researchers realized that the journey of an FRB through space contains something almost like a receipt. As the radio pulse crosses the tenuous ionized material between galaxies, different frequencies arrive at slightly different times. The delay tells us how many free electrons the signal passed through. And those electrons let us weigh matter that is otherwise almost invisible. In 2025, a large sample of localized fast radio bursts allowed researchers to make one of the clearest inventories yet of where ordinary matter is hiding. The result was remarkable. Most of the missing baryons were not locked inside stars. They were not hiding inside galaxies. They were spread through the enormous diffuse web between galaxies, a cosmic fog, thin almost beyond imagination, yet containing a vast fraction of the ordinary matter in the universe. I want to be precise. Scientists had already accumulated evidence for missing baryons in the intergalactic medium before this work. This was not the first clue. What changed was the quality of the accounting. Fast radio bursts made it possible to partition the cosmic baryon budget with unprecedented directness. The jar had not been leaking, and the water had become mist. So that is the door. And tonight, I want to show you how a flash lasting only a thousandth of a second helped solve a mystery stretching across billions of light years. Before we step through that door together, take a moment to subscribe to Deep Field Lecture. If you want to explore the places where the universe hides its answers in plain sight, you are in the exact right place. Now, I want you to imagine an old accountant's ledger. On the left page is a prediction. On the right page is what you can actually count. The universe gives us both. The prediction comes from the earliest moments of cosmic history. During the first few minutes after the Big Bang, the universe was hot enough for nuclear reactions to build the lightest atomic nuclei, hydrogen, helium, small amounts of deuterium and lithium. The relative abundances of these elements depend sensitively on how much ordinary matter, or baryonic matter, existed at the time. Later, roughly 380,000 years after the Big Bang, the universe cooled enough for electrons and nuclei to combine into neutral atoms. Light could finally travel freely. We observe that ancient light today is the cosmic microwave background. Tiny fluctuations in its temperature and polarization encode information about the contents of the universe. From these measurements, cosmologists can infer the density of baryonic matter with extraordinary precision. The ledger's left page is remarkably clear. Only a small fraction of the total cosmic energy budget is ordinary matter. Most matter is dark matter. And an even larger share of the present cosmic energy budget is attributed to dark energy. But ordinary matter is the portion we know most intimately. It is the matter of chemistry, the matter of biology, the matter of every telescope we have ever built. So you might think it would be the easiest component to find. It was not. When astronomers added up the baryons locked in stars and the gas that could readily observe in and around galaxies, the total came up short. The missing fraction changed as observations improved, but for a long period, a large amount of ordinary matter at relatively recent cosmic times remained difficult to identify directly. And this became known as the missing baryon problem. Hold on to the ledger. Nothing in the physics required the baryons to disappear. Conservation had not failed. The problem was observational. Where had the matter gone? The leading expectation was that much of it occupied the intergalactic medium, especially warm and hot diffuse gas distributed through the cosmic web. But the intergalactic medium is extraordinarily thin. The average density between galaxies can be so low that ordinary techniques struggle to detect it. Imagine trying to find smoke in a stadium after a single match has burned at one end. The smoke is there, but spread it over a large enough volume, and every cubic meter contains almost nothing. That is the first reason the matter became invisible. The second is temperature. Gas in the cosmic web can be heated as structure forms. Matter falls into filaments and halos. Gravity accelerates it. Shocks raise its temperature. Some of this material becomes warm, hot intergalactic medium with temperatures spanning roughly hundreds of thousands to millions of degrees. That sounds easy to detect. Hot things glow, but density matters. A plasma can be hot and still radiate very weakly if there are too few particles colliding. The universe had hidden matter not by making it exotic, but by making it diffuse. This is one of the most elegant tricks nature plays. Sometimes invisibility is not about darkness, it is about dilution. Here is the hard truth: a single cubic meter of intergalactic space can contain vastly fewer particles than the best vacuum chambers humans build on Earth. And yet, multiply that tiny density across the immense volume between galaxies, and the total mass becomes enormous. A teaspoon can look empty. An ocean made from teaspoons is not. To understand how astronomers finally weighed this fog, I want you to imagine a race. Two runners leave a distant city at the exact same moment. One takes a perfectly clear road, the other moves through a thin field of resistance. The resistance is tiny, almost negligible, but the road is billions of kilometers long. And by the time the runners arrive, a measurable gap has opened between them. Radio waves traveling through ionized gas behave in a related way. A fast radio burst emits radiation across a range of radio frequencies. As those waves travel through plasma, lower frequency waves are delayed slightly more than higher frequency waves. This phenomenon is called dispersion. The amount of delay depends on the integrated number of free electrons along the line of sight. Astronomers quantify this using something called the dispersion measure. A fast radio burst, therefore, does not merely announce that something violent happened in a distant galaxy. Its pulse becomes a probe. Every free electron between the source and Earth leaves a tiny imprint on the arrival time. The universe writes its density into the signal. Hold on to that image. The FRB is a messenger carrying a passport filled with stamps. One stamp from the host galaxy, one from material around the source, one from the intergalactic medium, one from our own Milky Way. If astronomers can determine where the burst came from, they can begin separating those contributions. And that is why localization matters so much. A radio burst without a known host galaxy gives you a signal, but an uncertain distance. A localized burst gives you both. You can identify its galaxy, measure the galaxy's redshift, estimate how far back in cosmic history the signal originated, then compare the dispersion measure with the amount expected from intervening matter. Do this once and you learn something. Do it dozens of times across many lines of sight, and you begin tomography. The universe becomes weighable. This is the moment everything changes. Fast radio bursts were first discovered as mysterious transient signals. They lasted milliseconds. Their origins were uncertain. Some repeated, others appeared only once. Astronomers debated whether they were local, extragalactic, or even instrumental artifacts in the earliest years. And then the field matured. Bursts were localized to host galaxies. A repeating FRB was found associated with a persistent radio source. A powerful radio burst from a galactic magnetar linked at least some FRB like phenomena to highly magnetized neutron stars. The mystery of their origins has not vanished completely, but the signals became useful even before every source mechanism was understood. That is a recurring pattern in science. You do not need to understand the lighthouse's machinery to navigate by its beam. FRBs became cosmic lighthouses, and their dispersion became a ruler for invisible matter. In 2025, researchers using the Deep Synoptic Array and a large set of localized bursts assembled a much stronger census of baryons across cosmic distances. And the study found that roughly three-quarters of ordinary matter was in the intergalactic medium. Another substantial fraction occupied the circumgalactic medium, the enormous halos of gas surrounding galaxies. Only a relatively small share was concentrated in stars and the dense gas we more easily associate with galaxies. Think about the sheer weight of that. The universe we see in astronomical photographs is visually dominated by stars and galaxies. But most ordinary matter is not inside the luminous structures, it is between them. The bright universe is not where most baryons live. The darkness between galaxies is not empty, it is the main reservoir. I want you to look around the room you're sitting in right now, and your intuition was built in an environment where matter is concentrated. Walls, tables, air, bodies, rocks, water, and we therefore associate physical importance with density. The cosmos does not share that bias. A region can appear nearly empty and still dominate the mass budget if it occupies enough volume. And this is why the cosmic web matters. Imagine a sponge. Dense material forms the strands and intersections. Large cavities occupy most of the volume. Now stretch that sponge across hundreds of millions of light years. Galaxies gather preferentially along filaments and at nodes. Clusters form where the web is densest. Between them runs diffuse gas. Some gas hosts galaxies in the circumgalactic medium. Some fills the intergalactic filaments. The universe is not a collection of isolated islands. It is an ecosystem of connected reservoirs. For decades, astronomy was naturally biased toward the islands because islands shine. Fast radio bursts let us weigh the sea, and now something beautiful happens. The mystery of missing matter turns into a map of feedback. And where baryons live tells us how galaxies evolved. Stars form from gas, supernovae explode and push gas outward. Growing black holes can launch winds and jets powerful enough to expel material from galaxies. Gravity pulls matter inward, feedback pushes it outward. The balance determines how much gas remains inside galaxies, how much surrounds them, and how much is thrown into the wider intergalactic medium. So, locating the missing baryons is not merely an accounting exercise, it tells us about the history of cosmic violence. Every baryon outside a galaxy may carry a story. Perhaps it was never captured. Perhaps it fell inward and was later expelled. Perhaps a supermassive black hole heated it. Perhaps stellar winds moved it. Perhaps shocks in the cosmic web raised its temperature. The baryon census becomes an archaeological record of galaxy formation. This is why the 2025 result matters beyond the phrase mystery solved. The answer creates a deeper question. How did the matter get there? And the universe does this repeatedly. You find a missing object, then you discover that its location is evidence. Return to the jar. At first, you only want to know where the water went. Now you discover that the water is coating the walls as microscopic droplets. Immediately, a new question appears. What process turned liquid into mist? In cosmology, that process is baryonic feedback, and feedback is one of the most challenging ingredients in simulations of galaxy formation. Dark matter is comparatively straightforward tomorrow-gravitationally. Ordinary gas is difficult, and it cools and it heats It forms stars. It interacts with radiation. It develops magnetic fields. It is accelerated by supernova explosions. It falls into black holes. It can be driven outward by active galactic nuclei. Small scale processes can affect enormous structures. This is why cosmological simulations require subgrid models and enormous computational effort. You cannot simulate every atom in a galaxy. You approximate the collective effects of star formation and feedback, and then you compare the synthetic universe with the real one. The distribution of baryons becomes one of the hardest tests. If a simulation leaves too much gas in galaxies, feedback may be too weak. And if it ejects too much, feedback may be too strong. If circumgalactic halos contain the wrong amount, something in the transport physics is missing. FRBs provide a new measurement of that distribution. The coin is rigged, not because the laws are failing, because the signal contains more information than the eye can see. The arrival time sweep of a millisecond pulse can tell us about matter spread across billions of light years. There is something almost absurd about the mismatch of scale, a burst shorter than a blink, a journey longer than human civilization can intuitively comprehend. And hidden inside the difference between low and high radio frequencies is the mass of the cosmic web. This is where human intuition entirely breaks down. You might think that to weigh the universe, you need to see the matter. Physics says no, you need an interaction. Gravity reveals dark matter. Dispersion reveals free electrons. Gravitational lensing reveals total mass. Absorption lines reveal gas. X-rays reveal hot plasma. The universe can be invisible in one language and obvious in another. Science advances by learning new languages. For centuries, astronomy was visible light. Then radio astronomy opened a hidden sky. X-rays revealed black holes, neutron stars, and million-degree plasma. Infrared telescopes penetrated dust and reached high redshift galaxies. Gravitational waves let us detect space-time itself changing shape. Fast radio bursts now turn radio dispersion into a baryon scale. Each new messenger exposes a universe that was always present. We were simply deaf to it. There is an important distinction here. The missing baryon problem is not the dark matter problem. They are often confused because both involve missing mass. Baryonic matter is ordinary matter composed primarily of protons and neutrons. We understand its particle identity. Dark matter is a separate component whose microscopic identity remains unknown. Finding the missing baryons, therefore, does not solve dark matter. It does not reduce the need for dark matter. It solves a different accounting problem. The early universe predicted a certain amount of ordinary matter. We could not locate much of it at later epochs. Now, FRB measurements strongly support the conclusion that the missing component is largely distributed through diffuse intergalactic gas. The cosmic ledger balances much more cleanly, but dark matter remains on another page entirely. That distinction makes the result even more satisfying. We did not need a new particle, we needed a new flashlight, or more precisely, a new backlight. Fast radio bursts illuminate the fog from behind. Imagine walking through a valley before sunrise. You cannot see the mist. Then a car approaches from the other side. Its headlights scatter through the air, and suddenly the fog becomes obvious. The headlights did not create the mist, they revealed it. FRBs do something analogous on cosmic scales. Their radio waves travel through free electrons and arrive altered. The alteration is the evidence. And because the bursts originate at different distances and directions, each becomes another line through the cosmic fog. With enough lines, astronomers can begin reconstructing how baryons are distributed. This is one reason the future of FRB astronomy is so exciting. More localized bursts mean better statistics. Better statistics means smaller uncertainty. Smaller uncertainty means more than simply knowing where the missing baryons are. It means using them to test cosmology. FRBs can potentially help probe the distribution of matter, galaxy halos, magnetic fields, turbulence, reionization, and even aspects of the expansion history. A mysterious phenomenon becomes infrastructure. That transformation is one of my favorite things in science. The anomaly becomes the instrument. Think of pulsars. When the first rapidly repeating radio source was discovered, its regularity was so unusual that the possibility of extraterrestrial intelligence briefly entered the conversation. We now know pulsars are rotating neutron stars, and their extraordinary regularity makes them some of the finest clocks in nature. Arrays of pulsars are now being used to detect low frequency gravitational wave backgrounds. The mystery became a ruler. Fast radio bursts may be following the same path. First, what are these flashes? And then, where do they come from? Now, what can they tell us about everything between us and them? This is the zoom out. Science does not merely solve mysteries, and it recycles them into tools. Now, I want you to imagine the cosmic web again, but remove every star, remove every galaxy, remove every glowing nebula, leave only the baryons spread between them. The image would appear nearly black to your eyes, yet much of ordinary matter would still be there. This is the universe stripped of its visual bias. Most baryons are not assembled into luminous objects that dominate our photographs. They occupy environments so thin that a human observer floating inside them would experience something close to perfect vacuum. And still, this diffuse matter matters enormously. It carries metals expelled by galaxies. It records heating from structure formation. It responds to energetic feedback from black holes. It feeds galaxies with fresh material. It participates in the cycle through which galaxies grow and evolve. The intergalactic medium is not empty background. It is part of the machinery. Hold on to the old watch. In earlier lectures, I have used a watch as a metaphor for physical theories, gears hidden beneath a visible face. Here, the cosmic web is the mechanism beneath the luminous universe. Stars are the hands, galaxies are the numerals, but the gas between them is part of the gear train. Ignore it, and the clock appears incomplete. Find it, and the machine begins to make sense. Here's the hard truth, and the universe is mostly not where the light is. That statement applies to dark matter. It applies to diffuse baryons, and in another sense, it applies to knowledge itself. The most obvious objects are not always the most important reservoirs. Astronomy began by cataloging bright things because bright things are easy to find. Modern cosmology increasingly measures what cannot be seen directly: invisible mass, invisible gas, invisible fields, expansion inferred from redshifts, primordial fluctuations encoded in microwaves. The history of the universe is reconstructed from indirect evidence because indirect evidence is often the only evidence nature offers. That is not a weakness, it is what physics is. You have never seen gravity itself. You see falling objects, and you have never seen an electron as a tiny ball with your eyes. You infer its properties through interactions. You have never touched space time curvature. You measure clocks, trajectories, and waves. Science does not require reality to present itself visually, and it requires consistency. And FRBs give us a beautiful example. The dispersion of the signal depends on electron density. Electron density connects to ionized baryonic matter. Redshift gives distance information. Host galaxy localization separates source contributions. Statistical samples reveal the average distribution. Independent cosmological measurements predict the total baryon abundance. The pieces meet, and when independently derived numbers converge, confidence grows. That convergence is the real meaning of solved, not that no question remains, not that every baryon has been assigned a street address. But that the decades old discrepancy now has a compelling observational explanation. Most of the missing ordinary matter is hiding in the thin gas between galaxies and around them. The cosmic fog was real. We simply needed the right signals passing through it. Now consider how strange the historical arc is. The Big Bang predicted matter. Galaxies failed to contain enough. Simulations predicted hot diffuse gas. Direct detection was difficult. Then mysterious millisecond radio flashes appeared from across the cosmos. Those flashes were localized. Their frequency-dependent delays became measurements of electron columns. And suddenly, an entirely different mystery helped solve the baryon problem. The universe connected two questions that initially seemed unrelated. What causes fast radio bursts? Where is the missing matter? You do not need the complete answer to the first question to use FRBs against the second. Science is full of these cross connections, so a tool invented for one purpose becomes decisive somewhere else. The cosmic microwave background was once unwanted noise in a radio antenna. Gravitational lensing, predicted by relativity, became a map of dark matter. Supernova explosions became rulers for discovering cosmic acceleration. Quasars became flashlights for studying intergalactic gas. FRBs have become way stations. Nature does not divide itself into our academic departments. The same signal can belong to stellar astrophysics, plasma physics, cosmology, and fundamental physics at once. And that is why curiosity is so productive. You never know which mystery will become the instrument for another. I want you to look at your hand one more time. The protons and neutrons inside it belong to the same baryonic family. As the missing matter spread through intergalactic space, chemically, your body is a dense island. Cosmically, it is an exception. Most baryons never became people. Most never became planets. Most never became stars. They drift in the web. Thin, hot, ionized, almost invisible. There is a humility in knowing that, and we naturally tell the story of the universe through objects like ourselves. Stars matter because they shine. Planets matter because they are solid. Galaxies matter because they are magnificent. But the majority of ordinary matter does not participate in those visually dramatic forms. Reality is not obligated to concentrate itself for our convenience. The baryons between galaxies are a reminder that existence does not require spectacle. Sometimes the largest reservoir is the faintest one. Newton taught us to infer an invisible force from visible motion. Maxwell taught us that light belongs to an electromagnetic spectrum far larger than human vision. Einstein taught us to treat space-time geometry as physical. Quantum mechanics force us to abandon classical intuition at microscopic scales. Modern cosmology now asks us to accept another inversion. Empty space is not empty. The darkness between galaxies contains structure, gas, plasma, magnetic fields, dark matter, radiation, a fossil record of cosmic evolution. And with the right instrument, even a millisecond flash can reveal it. Now it is our turn. The next stage of this story is not simply finding the missing baryons, it is mapping them. How do baryons move between galaxies and the intergalactic medium? How much material is expelled by black holes? How much remains bound in halos? How does this change with galaxy mass? How does the distribution evolve with cosmic time? How magnetized is the cosmic web? How turbulent is it? How accurately can FRBs measure the baryon content along individual sight lines? Can we combine FRB dispersion with X-ray, ultraviolet, and gravitational lensing observations to build a three-dimensional picture? And these are not small questions. They connect the life cycle of galaxies to the global matter budget of the universe. The solved mystery becomes a new field of measurement. Journeys like this, deep into the bleeding edge of human knowledge, require time, deep focus, and a relentless dedication to distinguishing what the evidence actually establishes from what the headline implies. Below this video, you will see a button labeled Super Thanks. If you choose to support the channel there, you help make these long-form explorations possible. But before we end, return with me to the objects we carried through this journey. The seal jar taught us that matter can be present even when we cannot see where it went. The accountant's ledger taught us that the early universe had already told us how much ordinary matter should exist. The stadium smoke taught us how dilution can create invisibility. The two runners taught us how plasma delays radio frequencies. The stamp passport taught us how an FRB records the matter along its journey. The sponge showed us the cosmic web, and the headlights in the fog showed us what fast radio bursts finally became. Backlights. Scientists did not discover that the missing matter had escaped the universe. They discovered that our eyes had been looking in the wrong places. Much of the ordinary matter was never hidden inside some exotic dimension. It was stretched through the space between galaxies, too thin to shine brightly, too hot and diffuse to inventory easily, but not too invisible to alter a radio pulse. A burst lasts a millisecond. The fog extends for billions of light years, and somehow, across that impossible difference in scale, the universe leaves enough evidence for us to weigh what we cannot see. That is the mystery we finally began to close, and it leaves us with one final question. If the emptiest looking parts of the cosmos can hide most of its ordinary matter, what else have we been calling empty simply because we have not yet learned how to measure it?